Across the United States, public attention often turns toward famous earthquake zones such as California's San Andreas Fault or the Cascadia Subduction Zone in the Pacific Northwest. Far less recognized is another immense fault system extending through the heart of the American West, running alongside cities where millions of people live, work, and raise their families every day. Why has one of the nation's longest continuous active faults remained relatively unknown outside scientific circles, despite its extraordinary length? Why do the towering Wasatch Mountains continue rising while the broad valleys beside them gradually sink? Most importantly, what does it mean when an entire metropolitan corridor has developed within reach of a fault that has repeatedly produced powerful earthquakes over thousands of years? Running for approximately 213 to 230 miles, or about 343 to 370 kilometers, across northern and central Utah, the Wasatch Fault is recognized as the longest continuous active normal fault in the United States. Rather than marking the collision of tectonic plates like many of the world's most famous earthquake zones, the Wasatch Fault exists because the Earth's crust in this part of North America is gradually being stretched apart. That slow but relentless extension has shaped Utah's landscape for millions of years, lifting dramatic mountain ranges while lowering adjacent valleys and creating one of the continent's most recognizable landscapes. Its influence extends far beyond geology textbooks. Nearly every major city along Utah's densely populated Wasatch Front lies close to one or more segments of this fault system. Salt Lake City, Ogden, Provo, Layton, Sandy, West Valley City, Orem, and dozens of neighboring communities occupy ground that owes its existence to repeated movements along the Wasatch Fault. Collectively, these urban centers are home to well over 2 million residents, representing the overwhelming majority of Utah's population. For many people, the Wasatch Mountains symbolize recreation, scenic beauty, and world-class skiing. Their steep peaks attract hikers, climbers, mountain bikers, and winter sports enthusiasts from around the globe. Less obvious is the geological engine responsible for creating those mountains in the first place. Every towering ridge, dramatic canyon, and broad valley visible today reflects countless episodes of crustal movement accumulated over millions of years. Unlike transform faults, where blocks of crust slide horizontally past one another, or subduction zones, where one tectonic plate dives beneath another, the Wasatch Fault belongs to a category known as a normal fault. In this type of faulting, the crust is pulled apart rather than compressed. As tension increases, one side of the fault gradually drops downward relative to the other. The process resembles stretching a thick piece of brittle material until fractures develop and individual blocks begin moving vertically. Although that description sounds simple, the forces responsible operate across an enormous region covering much of the western United States. The Wasatch Fault forms part of the Basin and Range Province, one of Earth's largest regions undergoing continental extension. Stretching from eastern California across Nevada and into Utah and beyond, this immense geological province has experienced crustal stretching for roughly the past 17 million years. Scientists continue studying exactly why this extension developed, but several interacting processes appear responsible. Deep within the Earth's mantle, changes in convection, variations in crustal thickness, and evolving plate motions have gradually altered the stress field affecting western North America. Instead of squeezing the crust together, these forces slowly pull it apart. Although the rate of stretching appears almost unimaginably slow on a human timescale, the cumulative effects become extraordinary over millions of years. Crust that once formed a relatively broad, elevated plateau gradually fractured into countless elongated mountain ranges, separated by equally elongated valleys. Nevada became famous for this pattern of alternating basins and ranges, but Utah displays some of the most striking examples as well. The Wasatch Fault occupies the eastern edge of the Basin and Range Province. To its east lies the comparatively stable Colorado Plateau, while to its west the stretched crust of the Basin and Range continues across hundreds of miles. This transition between two very different geological provinces helps explain why deformation becomes concentrated along the Wasatch Fault. Imagine attempting to slowly pull apart a thick sheet of hard candy. Rather than stretching evenly everywhere, cracks tend to form along specific zones where the material is weakest. Something similar occurs within Earth's crust. Instead of extending uniformly across the region, deformation becomes focused along major fault systems capable of accommodating the movement. The Wasatch Fault serves as one of those principal zones. Over millions of years, repeated earthquakes have allowed the western side of the fault to sink, while the eastern side remained comparatively elevated. Each major rupture contributes only a modest amount of displacement, perhaps several feet or a few meters during an individual event. Yet when those offsets accumulate across hundreds of thousands or millions of earthquakes over geological time, entire mountain ranges emerge. This long-term process explains why the Wasatch Mountains rise so abruptly above the Salt Lake Valley. Their impressive relief did not develop because the mountains were pushed upward like wrinkles in a rug. Instead, much of the dramatic elevation difference reflects the valley floor gradually dropping relative to the mountain block during repeated fault movements. Geologists refer to the elevated block as the footwall and the lowered block as the hanging wall. Along the Wasatch Fault, the mountains occupy the footwall while the valleys generally form part of the hanging wall. Every significant earthquake contributes another incremental adjustment between these enormous crustal blocks. That relationship also explains the remarkably straight mountain front extending along much of northern Utah. Rivers descending from the mountains carve deep canyons, yet the mountain front itself remains sharply defined because repeated fault movement continually rejuvenates the landscape. Without ongoing uplift, erosion would gradually wear down the mountains and soften the dramatic transition between peaks and valleys. Instead, uplift and erosion remain locked in a continuous geological competition. Streams flowing from the Wasatch Mountains transport enormous quantities of rock, gravel, and sediment into adjacent valleys. Over time, these materials spread outward to form broad alluvial fans at canyon mouths. Cities throughout the Wasatch Front have expanded across many of these ancient deposits because they provide relatively stable terrain for development. However, the same deposits can amplify earthquake shaking under certain conditions compared with harder bedrock found higher in the mountains. This combination of active faulting, soft sediments, and dense urban development has attracted intense scientific attention for decades. Researchers have devoted extraordinary effort to reconstructing the Wasatch Fault's earthquake history. Because written records extend back only a tiny fraction of the fault's lifespan, scientists rely on paleoseismology, the study of prehistoric earthquakes preserved within the landscape itself. Across selected locations, researchers excavate deep trenches across the fault trace. These trenches expose layers of sediment that accumulated over thousands of years. When a large earthquake ruptures the surface, younger sediments become displaced relative to older ones. By carefully mapping these offsets and dating organic material buried within successive layers, scientists can estimate when previous earthquakes occurred. The resulting record reveals that the Wasatch Fault has generated numerous powerful earthquakes during the past several thousand years. Interestingly, the fault does not usually rupture from one end to the other during a single earthquake. Instead, it consists of several distinct segments, each capable of producing major seismic events independently. Among the principal segments identified by researchers are the Brigham City, Weber, Salt Lake City, Provo, Nephi, and Levin segments, along with additional southern sections. Each possesses its own geological history, recurrence interval, and pattern of prehistoric ruptures. This segmentation has important implications. Stress released during one earthquake may not eliminate accumulated strain elsewhere along the fault. One segment can remain quiet while another experiences repeated activity. Over centuries, stress continually redistributes throughout the fault system, creating a complex pattern that scientists continue working to understand. Although individual segments behave somewhat independently, they are not completely isolated. Large earthquakes alter stresses throughout neighboring portions of the crust, sometimes increasing or decreasing the likelihood of future ruptures elsewhere. Understanding those interactions remains one of the most active areas of earthquake research. Modern monitoring networks now surround the Wasatch Fault with remarkable precision. Hundreds of sensitive instruments continuously record even tiny earthquakes too small for people to feel. High-precision global positioning system stations measure crustal motion down to fractions of an inch or mere millimeters, documenting the slow accumulation of tectonic strain year after year. These measurements consistently demonstrate that the region remains tectonically active. The movement occurs so slowly that no individual notices it during daily life. Fingernails grow faster than the crust moves along much of the fault. Yet geological time transforms those almost imperceptible motions into enormous landscape changes. Every passing century stores additional elastic energy within rocks bordering the fault. Rather than moving smoothly every day, sections of the fault often remain locked by friction. While locked, surrounding rocks continue deforming under tectonic forces. Stress accumulates much like tension building within an increasingly stretched spring. Eventually, the strength of the rocks can no longer resist the accumulated forces. At that instant, stored energy releases almost simultaneously as the fault slips. The sudden movement sends seismic waves racing outward in every direction, producing the earthquake shaking experienced at the surface. This cycle of gradual strain accumulation followed by abrupt release defines earthquake generation not only along the Wasatch Fault, but across active fault systems throughout the world. One common misconception assumes that an absence of recent large earthquakes indicates declining danger. Geological evidence suggests the opposite can often be true. Long, quiet intervals frequently represent periods during which stress continues accumulating rather than disappearing. For the Wasatch Fault, that reality has motivated decades of increasingly sophisticated research. Scientists recognize that understanding the fault's past offers one of the best windows into its future behavior. Every trench excavated, every sediment layer analyzed, every precise elevation measurement collected, and every tiny earthquake recorded contributes another piece to a geological puzzle spanning millions of years. That puzzle extends beyond the fault itself. It reaches into the rapidly growing communities spread across northern Utah, where expanding neighborhoods, transportation corridors, schools, hospitals, airports, water systems, electrical infrastructure, and businesses have all developed within a landscape whose defining features were created by repeated earthquakes. The same forces that raised the spectacular Wasatch Mountains and carved the valleys supporting modern civilization continue operating today, silently reshaping the region at a pace measured not in days or years, but across generations and geological ages. One reason the Wasatch Fault commands sustained scientific attention is the size of the earthquakes it is capable of producing. Geological evidence indicates that individual fault segments have generated earthquakes approaching the upper magnitude 6 range to around magnitude 7.5. While those numbers may appear modest compared with the largest earthquakes ever recorded along subduction zones, they represent events capable of causing widespread destruction, especially when they occur close to densely populated areas. Unlike earthquakes that strike far offshore or in sparsely inhabited deserts, a major rupture along the Wasatch Fault would unfold directly adjacent to Utah's principal urban corridor. The Wasatch Front has experienced extraordinary population growth over recent decades. Communities that once consisted of isolated farming towns have expanded into a nearly continuous chain of cities stretching from Brigham City through Ogden, Salt Lake City, Provo, and farther south. Highways, commuter rail lines, airports, industrial districts, universities, hospitals, and residential neighborhoods now occupy ground that has repeatedly moved during prehistoric earthquakes. This concentration of people and infrastructure is one reason emergency planners consider the Wasatch Fault among the nation's highest seismic risks. Risk is determined by more than the probability of an earthquake. Scientists often describe seismic risk as the combination of hazard, exposure, and vulnerability. The hazard comes from the fault itself and its ability to generate strong ground shaking. Exposure reflects the number of people, buildings, roads, utilities, and critical facilities located within the affected region. Vulnerability depends on how well those structures can withstand earthquake forces. Along the Wasatch Front, all three factors intersect. The fault is active, Millions of residents live nearby, and portions of the urban landscape include buildings constructed before modern seismic design standards became widespread. Although many newer structures incorporate earthquake-resistant engineering, older masonry buildings remain common in parts of Utah's historic downtown districts. Scientists have also identified another important challenge that extends beyond the fault trace itself. Earthquake damage is rarely confined to locations directly above the rupture. Seismic waves travel through surrounding rocks and sediments, often producing unexpectedly strong shaking many miles away. Much of the Wasatch Front is built upon thick layers of unconsolidated sediment deposited by ancient lakes, rivers, and glaciers. These deposits differ significantly from solid bedrock exposed within the nearby mountains. Buildings constructed atop these sediments may therefore experience stronger or longer-lasting shaking than similar buildings founded directly on bedrock. One ancient lake plays a particularly important role in shaping these geological conditions. During the last ice age, much of western Utah lay beneath the enormous freshwater body known as Lake Bonneville. At its maximum extent, this prehistoric lake covered approximately 20,000 square miles, or more than 51,000 square kilometers. It reached depths exceeding 1,000 feet, or about 300 meters, across portions of the basin. For thousands of years, rivers flowing into Lake Bonneville carried enormous quantities of sand, silt, clay, and gravel. As the lake eventually receded, it left behind extensive sedimentary deposits that now underlie many of Utah's largest communities. Those sediments preserve an extraordinary record of ancient environments, but they also influence modern earthquake hazards. Fine-grained lake deposits often respond differently to seismic shaking than coarse gravels or exposed bedrock. Engineers carefully evaluate these differences when designing buildings, bridges, and transportation systems because local ground conditions can significantly alter earthquake performance. Another concern involves liquefaction. Liquefaction occurs when water-saturated sandy soils temporarily lose much of their strength during intense shaking. Instead of behaving like firm ground, the sediments may briefly act more like a liquid suspension. Buildings can tilt, pipelines may float upward, roads may buckle, and buried infrastructure may shift unexpectedly. Not every earthquake produces liquefaction, and not every location contains susceptible soils. Nevertheless, portions of the Wasatch Front possess the combination of young sediments and groundwater conditions that make liquefaction an important consideration during seismic planning. Surface fault rupture presents an additional hazard. Many earthquakes generate shaking without visibly breaking the ground surface. However, sufficiently large earthquakes along the Wasatch Fault have repeatedly produced measurable offsets where one side of the fault moves vertically relative to the other. Imagine standing along a road that crosses the fault just as a major rupture occurs. Instead of remaining level, one side of the road might suddenly stand several feet or more than 1 meter higher than the opposite side. Such displacement would severely damage roads, railways, pipelines, canals, and buried utilities crossing the fault zone. For that reason, geologists have spent decades mapping the precise locations of active fault traces. These detailed maps help planners reduce the likelihood of constructing critical facilities directly across the portions of the fault most likely to rupture during future earthquakes. The Wasatch Fault also provides scientists with a remarkable natural laboratory for studying earthquake recurrence. Unlike faults that remain concealed deep underground, large sections of the Wasatch Fault leave clear evidence across the landscape. Distinct fault scarps, offset stream channels, displaced sediment layers, and uplifted landforms allow researchers to reconstruct thousands of years of seismic history. One recurring question involves whether earthquakes occur according to a predictable schedule. The answer is more complicated than many people expect. Although geological records reveal approximate average recurrence intervals for individual fault segments, earthquakes do not operate according to calendars. An average interval does not mean a major earthquake arrives precisely after a certain number of years. Instead, it represents the long-term average between many prehistoric events, each separated by varying lengths of time. Some intervals have been considerably shorter than the average, while others have been much longer. This variability reflects the complexity of stress accumulation throughout Earth's crust. Numerous geological factors influence exactly when a locked fault finally ruptures, many of which remain impossible to measure directly. That uncertainty explains why scientists do not attempt to predict the exact month or year of future earthquakes. Instead, researchers estimate probabilities over periods such as several decades. These probability assessments combine paleoseismic evidence, modern geodetic measurements, fault mechanics, and statistical modeling to estimate the likelihood that one or more fault segments will rupture within a given time frame. Even with increasingly sophisticated technology, forecasting earthquakes remains fundamentally different from forecasting weather. Meteorologists observe storms developing in real time through satellites and radar. Earthquake scientists, by contrast, cannot watch stress building miles beneath Earth's surface with comparable clarity. They infer the hidden processes using surface measurements, seismic monitoring, satellite observations, laboratory experiments, and computer simulations. Despite those limitations, scientific understanding of the Wasatch Fault has advanced dramatically over the past several decades. High-resolution airborne laser mapping, known as LiDAR, has revealed subtle fault scarps hidden beneath vegetation that earlier generations of researchers could scarcely detect. Satellite-based positioning systems continuously measure crustal deformation with astonishing precision, while increasingly sensitive seismic networks capture thousands of tiny earthquakes each year. Together, these technologies have transformed the Wasatch Fault into one of the best-studied active fault systems in North America. Yet every new discovery reinforces the same conclusion. The Wasatch Fault is not an ancient fracture that completed its work millions of years ago. It remains an active expression of the ongoing stretching of Western North America. The valleys continue to subside by tiny increments, tectonic stress continues to accumulate within the rocks, and the towering Wasatch Mountains continue their gradual rise as the landscape evolves through the same powerful geological forces that have shaped Utah for millions of years.